Hi again, everyone. Welcome back to the Italian C++ Conference 2020. I hope you're enjoying the conference so far. And we have Roy here. Hi, Roy. How things are going there?
Doing great. Thank you. Nice and sunny.
Nice. Okay, great. In Italy as well here, nice and sunny. I don't know why people are attending this conference instead of going to the sea. But anyway, no, don't ask this. We are all set for your session, so I leave the stage. I'll be here behind the scenes. I know that you are getting questions also during your talk, so I invite people attending on remote to ask questions on the Q&A section, and let them go. Okay, cheers. See you later.
Thank you. Thanks a lot. Hello, everyone. It's really great speaking here and talking with you. All the sessions so far today have been really cool, and I'm happy to share a little bit of my insights about concepts and writing libraries, and hopefully you'll find it interesting as well. So yeah, great. So let's get going. Hello, my name is Roy. I live in Israel, in Tel Aviv. I've been doing C++ for more than 20 years now, and currently I'm working for a company called Easter Research in Israel, doing finance, low latency trading. And if you're interested in coming to Israel and joining us, it'll be really cool. So to start off, my talk, is mainly around the concepts. So I'll just want to share a little bit from a long time ago, early 2013. Here's a short clip from Bjarne Strastrup when he presented to a group in A9 that contained Alex Stepanov as well, where he told us a little bit about what the importance of concepts are. Let's hear him out.
Concepts are fundamental. They're meant to represent fundamental concept in an application area. Alex has been saying this for at least 15 years. But
okay, so Alex, who's mentioned here, is Alex Stepanov, and here's even 8 years ago, Strastrup told us that concepts are fundamental, and the reason that it took it a long time to get to the standard C++20, but now it's here, so we need to learn what they are because they are important. And to give a short overview of why they're important, it has a lot to do with templates and overload resolution. I have to say that if you listen to some of the template talks even today, you've heard a lot about it, but maybe my take will give you some more insights. So to start off, just reminding everyone what templates are. It's basically a way to write a single function that will be applied to many, many types. Here's a short example, the min algorithm from STL, that can be applied to every type for which we can compare one another using the less than sign. And maybe we'll hear more about min later on from Walter E. Brown. And that's a basic use of a template. And there are many things to do with templates having to do with metaprogramming, where we can write different implementations and different pieces of code for the same algorithm that we want to write. So in this example here, we can see that we implement two different swap functions, one for any regular type, the other for arrays. And although they have the same meaning, they need to be implemented differently in C++. So, and the language gives us the overload resolution and a way to do it. There are some cases where we don't need to use template metaprogramming or any special tricks to get the right functionality and correct algorithm, but we want to use template and metaprogramming tricks to get a better performance, for example. So this is a rather convoluted piece of code. It uses a notion called enable if. It's inside the implementation of the fill algorithm in STL, where we can see that the implementer of STL wanted to make sure that if we're trying to fill an array of bytes, okay, then we're going to use memset instead of going through a loop and just applying the equal operator one after another to the entire array. Obviously, if we hadn't did this metaprogramming trick, the standard fill algorithm could have been optimized into a memset by the compiler. But this enable if trick is a metaprogramming trick that the STL implementer did in order to basically force the compiler, hey, for this case where we have an array of bytes, I want to use memset, and the compiler basically didn't have any way to get around it. So metaprogramming is a way for us to tell the compiler what we want if we have to. So that was a short introduction to give you a sense of where we are. And in this talk, I will basically introduce concepts, this new C++20 feature, and the ways and reasons why we want to use it. I will also show different alternatives of mechanisms that existed before concepts and how were they used and where were they used. I will share a lot of my opinions, a little bit of facts, but I'm really always willing to learn. I think you might disagree with my opinions, and I'll be very happy to hear what you think about them. So please ask questions. I'll be very happy to interact. I will give a few tips and ideas of the different mechanisms, what their strengths are and their weaknesses. And also give a few suggestions on places where I think C++ itself or the STL are suboptimal, and where I think maybe there's room for a change. Like I did so far, I will add some more code snippets from inside the STL itself, and I'll show some clips from YouTube to make things a little interesting. So to start off, let's get back to Strassrup, to the same talk that we've seen before. And let me see if I can also do something with the volume. And let's hear Strassrup tells us a little bit about what concepts actually are.
And the thing we were working on is it becomes a bunch of constant expressions. It becomes a bunch of Boolean expressions. Does this type have this property? Does the argument type has this property? Has the combination of types we get as arguments got this property? It's all predicates. It's all Boolean algebra. There's nothing about scopes, nothing about objects, nothing about indirect jump tables. It's all Boolean expressions.
Okay, so it's all Boolean expressions. Concepts are technically very easy to think about and to comprehend. They're just Boolean expressions over types. It's nothing too complicated once you realize what they are. And although it seems very simple, and sometimes very even similar to things that we had before, it still have different uses. So let's hear Strassrup again, another clip telling us what they are good for, or when should we use concepts.
You can overload if it meets the sets of constraints from one and not the other. That's the story. If they are subsets of each other, then it'll take the one the biggest one it can. In other words, if you most specific, well, the one that meets the largest number of the predicates.
Okay, so in here we heard from Strassrup that the main use case for using concepts has to do with overloading. Okay, overloading is something that existed in C++ since 1998 and even before. And the concepts are the way to make us or help tell the compiler which overload alternatives it should use over the other. And as Strassrup said, the compiler will pick the one that meets the largest number of predicates. Okay, let's leave Strassrup for a while, and I also want to share with you a few of the first paragraphs about concepts in the concepts library from cppReference.com. And these are long paragraphs. I won't read them all, but I do want to highlight a few points. It has to do about the relationship between syntax and semantics. If you recall, I think Sean Parent also discussed this a little bit this morning. We can see that the concepts in the standard have both syntax and semantic requirements. Okay, so syntax is about the way you write them and what's allowed in terms of the language, but semantics is also about the interpretation and the meaning of operations. And we can see in this last sentence that if a semantic requirement is not met at the point of use, the algorithm is ill-formed, no diagnostic requirement, and that's what we call undefined behavior. So it's also something that we need to remember when we use concepts, when we write our own concepts. We need to think about syntax and also semantics. And whenever we use a library that has semantic requirements, we have to very diligently keep in mind what their semantic requirements are, because otherwise our code will compile, but it will be undefined behavior. And actually, Sean Parent gave us a few examples earlier today. So to sum it all up, and this is basically the anchor of my talk today, concepts are relatively simple. It's a bunch of Boolean expressions, and we basically use them for overloading to take the overload that meets the largest number of predicates. And whenever we use them and think about them, we need to always keep in mind both the syntactic and the semantic parts of them. So now we'll just dive into these three different subjects and to give us a little bit more of an understanding of what they mean and what they are. So, by the way, if there are any questions, this might be a good time. I assume that we just started, but still, if anyone has any question, feel free to write them. I can also look at that right now. Okay, so let's dive into the first topic, a bunch of Boolean expressions. So for concepts, defining Boolean expressions is very, very easy. There are basically three ways to define concepts in C++. The first is just by declaring a concept is equal to some Boolean. Okay, so in this example, is integral v is a type trait, it's a Boolean, and I can just say that the integral concept is just equal to that Boolean. Okay, secondly, I can use Boolean algebra and Boolean expressions. Okay, so in this example, the signed integral concept is using the AND operator to take the integral concept and add an extra constraint using the is aligned v. Okay, so any Boolean algebra can be done on concepts. And the third and most unique way for defining concepts has to do with requires expressions. Okay, so requires expressions, that's a new keyword in the language. When we use requires for requires expressions, we basically can write arbitrary pieces of code inside the braces, and the compiler will basically try to see whether that code makes sense. The code will not actually be run or executed, but if the code is valid, if it can potentially be compiled, then this requires expression will be true. Otherwise, it will be false. So this is a way for us to very declaratively say what we want to do with our types, and if whatever we want to do is possible from the compiler standpoint, then the requires expression will be true. Otherwise, it will be false. And it's quite common to define concepts by using these requires expressions. I should also note that these clauses inside the braces, it can be not just about what code can be compiled and what cannot be, but it can also put some limits on the return values of the different expressions, etc. But you can look up the details later on. So these are the three basic mechanisms to declare concepts in C++20. And as far as you can see, this is a Boolean. This is quite simple. And not only that, it's actually also not so new. There were always ways to create Boolean expressions out of types even before C++20. So going all the way back to C++98, we had class templates that typically had the colon value member. I think you might have seen some examples even earlier today from Chris Van Rense's talk. And here we can see that bool constant is something that's commonly used in the STL. It's basically an integral constant, and we can define it to be either true or false. And then in C++14, I believe, we received the variable templates, which are const_expr Boolean variables that are also templated to types. And again, we can define them to be true, false, whatever we like. And there's also const_expr function templates that have the exact same functionality and can even be sometimes more complicated, templated on various different types. And this function template from I believe C++20 standard is called the isPointer interconvertible list class, is something that basically accepts two different classes and returns a Boolean expression. So we didn't really need concepts, and we had many ways to convert types into Booleans even before we had concepts. So there's nothing much new here. And I should also say that the entire expressiveness that we received with concepts was also available before. So Boolean expressions, as we've seen for concepts, is obviously viable and can be done without without concepts. Here we can see that the is-scalar type trait is basically an integral constant where they use a Boolean expression over other type traits to get and to understand whether a type is scalar or not. So Boolean expressions are allowed, and even the requires clause, which is a requires expression, which is new and novel. It basically we had ways to do it, even though it wasn't as nice of a syntax as it is right now. And the way typically it was used, it was with the concept of sphenae. You probably heard about it in other talks as well today. The substitution failure is not an error mechanism, and if you combine it together with the void t concept and type, and with the detection idiom, you can basically get a good amount of the power of requires expressions even before C++20. And this example over here is a short or is a pre-C++20 way to detect whether type T has a method called meow. Okay, so we can define it as something that is basically false for each and every type, and then using the void t and the decalval paren dot meow, we can check, does type T have a meow method that can be called, and if it does, then this specialization will take into effect, and has meow will become true for those types and those types only. So we didn't get a lot more power with concepts. It's but we could do a lot of it before, but still they have room in our language, and there are many things that we used to use these sphenae and void t before, where we will choose to use requires expressions and concepts today. We'll see where they are. Okay. I should also note that there's one specific way that existed before C++20 for templates, and actually is very, very special and unique with relation to concepts, and that specialization. Okay, so isConst is an example where we use the specialization to define which types are constant and not constant. We can see that the isConst is a template that is false for every type, and then we specialize them on const ones and define them to be true, and the compiler has ways to basically choose which is the most specialized out of different template specializations, and once it chooses the one that's most specialized, then that's the one that is used. And another mechanism that has to do with specialization is what I would call opt-in or opt-out. Okay, there are some places in the STL and in other libraries where a library will define some Boolean expression to be just plain false or plain true for some class R, with the intent that whoever uses the library itself can specialize and turn it into the other way around, into true or into false for their own uses. Okay, so enabled borrowed range is an example where it's generally false for every range that doesn't that we don't know anything different about, and whoever goes and implements their own ranges either inside the STL or outside the STL, they have the ability to specialize this Boolean for their own type of range and say that it's true if they know that they actually are a borrowed range. And this specialization mechanism has always existed. It's very, very strong. And it's interesting to note that as far as I know, concepts are the only template that cannot be specialized. Okay, so it's okay. It's possible to specialize class templates. It's okay to specialize variable templates. With functions, it's a little more tricky. It's actually overloading and not specialization, but technically it can be done. And or you can do at least you can do partial specialization, but you can do specific specialization. But concepts are a template that cannot be specialized. It's not possible to take a concept that was defined in a broad range and specialize it for specific types later on. But it's not very harmful. It's not very problematic, because as we saw, we can define concepts as equal to some other template, and if that other template can be specialized, then in fact we gain a lot of the power without needing to specialize the concept themselves. Okay, another mechanism that exists in STL, and it's not really 100% equivalent, but I decided to mention it just for full brevity, is traits classes. Okay, as you know, STL has iterator traits, allocator traits, and numeric limits is another trait class for numeric objects, and it's fully legal and fully expected for anyone who writes their own numeric object, such as maybe a temperature or some decimal type of numeric or anything else, to specialize their own instantiation of numeric limits and define various traits. Some are Boolean, some don't have to be for that type. So that's another mechanism that uses specialization, and again, not possible for concepts. Okay, so that was a brief overview of defining Boolean expressions over types. Should be quite straightforward. Before we dive into the second section, let's see if there are any questions or comments. Okay, let's move on. So now we'll talk about choosing overloads out of several candidates, and how the concepts are used to meet the ones with the largest number of predicates. So the basic idea here is about the interaction between a library and its application. Okay, if we think about it, one of the strengths of C++ is its ability to have libraries that interact with some user that hasn't even met the library author, and the types and the type mechanism are ways to ensure that the compiler will help us not misuse and use the library correctly. And whenever we find ourselves when one application uses a library written by someone else, there's the risk of problems, of errors, where the library expects one thing, the application expects another thing, and if the compiler will not help us, then we might find ourselves running into trouble at runtime in production, where it can be really problematic. And this is obviously, I think really makes sense, because different people have different assumptions. And people don't always read the documentation. So overload resolution is the basic way to try and verify that the expectations are matched. The overload resolution basically lets the library writer implement various different algorithms or different functionalities to their own algorithm, and even decide not to implement something, and let the compiler do the proper mix and match and the proper matching between what the application might want and what the library can provide. This can sometimes be like an on-off constraint to just disallow certain interactions, or more advanced mechanisms. So, for example, if I have a template function that only receives works on arrays or pointers, then the compiler will not let me pass something that isn't an array or a pointer. And if I have a function that has different implementations, then again, the compiler will choose the correct one out of an overload set. Okay, and there are some mechanisms that we'll see later on that can be easily bypassed. So if the application knows that the library expected one thing, and the compiler even tries to stop the application from misbehaving, in some cases there are ways or places where it's okay for the application to say, hey, I know what I'm doing, compiler, please let me do it. And other mechanisms are less negotiable, where if the application doesn't meet the exact requirements, then things won't work. A nice potential example of this before moving forward is the example that Sean Parent gave about the distance function in the STL, where the distance function itself receives two iterators and basically tries to find the distance between them. It never performs a dereference operation. Okay, and now the question arises, is it okay to call the distance function and give it two objects that cannot be dereferenced? Is it legal? Is it okay, etc.? And as Sean told us, it is not correct. Okay, so it shouldn't be bypassed. But until we had concepts, and even in STL right now, it can be bypassed. If you try to call the distance function with an object that cannot be dereferenced, it will work. It will give some some result, and hopefully whoever wrote the application knows what they're doing. It might just happen to work. Okay, so after we gave this overview, let's dive back into concepts. So the main way to perform overload resolution with concepts is by using what's called the requires clause. Okay, the requires clause uses the same keyword as requires, but it's not a requires expression. Requires clause is something that we attach to a function, to a class, to even a variable, and that is templated, and we constrain which template parameters can be used for that function or class or variable. There are various syntax alternatives on how to write it. You can use a requires clause in different places. You can avoid the writing requires, and instead just put the name of the concept that you want to require inside the template triangle brackets. And also use the auto syntax for that. But in general, that's that behind the scenes, what happens is a requires clause. And as Bjarne Strastrup mentioned, the most specialized version wins, meaning that if there are several overloads that have different requires clauses and different constraints, the compiler will try to basically order them, sort them by which is most specialized and which is less specialized. And there are very specific rules about it that you can look for the standard for details. It has to do with organizing the Boolean expressions as either a conjunctive normal form or disjunctive normal form. It's quite complicated, but in most cases, it's also quite intuitive. And where you see two concepts, you can usually try and see if there's one that's inherently more specialized than the other. And the compiler will allow an overload where there are multiple matches to exist, and it will just take the most specialized one when it chooses which overload to actually perform. All concepts are SFINE friendly, meaning that in case there are overloads that do not compile, cannot be substituted correctly, they're just removed from the set of candidates. They do not cause compiler errors by themselves. Only if all of the candidates that we're trying to match do not match, only then we will get a compiler error. But if at least one of the candidates matches, then it's fine. There will be no compiler error. We'll just take out of all the alternatives that are possible the one that is most specialized, and that's the one that we'll use. Another really strong point for using concepts is that it has very clear error messages. Typically, when we used to have template-related error messages in the past, it would really expose the code of the library in our face, because the compiler will really complain about specific line of code inside the library where it tries to do something with a template class and not able to do it. Whereas within concepts, it's typically much clearer, because the compiler really tries to match the type that we're trying to use the library with the concept that is constrained about, and will not even go into the actual code and implementation of the library in case of issues, and will just tell us which of the requirements in the concept are not met. So it's much simpler to read. Using concepts instead of SFINE, instead of other methods, usually has faster compilation times. So it's also a good bonus for using that. And so in general, it's really a rethinking of the most common mechanisms that's used by libraries so far into this one sort of like an attempt to be a silver bullet to use them. And in general, what we see with that is with this approach is that we received a new word in the language for defining requirements. Any library author can define their requirements, and the application must conform to those requirements. And especially the syntactic ones are checked by the compiler. And if the application code, the application class that we're trying to run the library with does not meet the requirements, there's no way around it. The compiler will not let us call a function that expects a specific concept with a class that does not meet the concept. Okay, so that's the basic way that we have right now in C++20 for the library to define requirements. Now let's look at alternatives that existed before concepts and before C++20. Again, let's hear a short clip from Timur Dumler from C++20 telling us how things used to be before concepts.
Let's remember if we let's see if we can remember how to use std enable if. Okay, so you can write the std enable if integral type and floating point type. Where do we put this? This is something that I can never remember, right? So you can put this onto the return type of the function, but then you don't really see the actual return type anymore, so that's not great. You can put this into the parameter list, but then you don't really see the parameter list anymore. So I don't like either of these. So my favorite method is actually to put this into the template argument list, because then you can still cleanly see the function signature. So that's, I think, the most readable way of doing this, except it doesn't work. Because it turns out that in C++, defaulted template arguments are not part of the function signature. And then you again have the same function signature twice, and then you again get this error redefinition of function template. Turns out you can work around that because that rule doesn't apply to non-type template parameters. So you can make this an int template parameter.
Okay, so that was Timur Dumler. You can find his talk on YouTube. I don't think you have to remember much about what he said, except that it was very, very complicated. So the main alternative to a requires clause before C++20 was using enable if and spine, and it was really complicated. And even the experts didn't really remember the exact way to do it. It was really tricky stuff. And that was also a library-based approach. The library author wrote their enable if clauses, and you had to basically abide by the requirements that were given to it. Aside from concepts and spine, which are library dependent approaches, there are other methods. But I should also say, by the way, that the enable if doesn't have any ranking by the compiler. If you have multiple overloads with enable if, only one has to be valid for any template that you use. If you try to have an overload with a type where two of the enable if conditions are met, the compiler will not try to rank it. It will just cause a compilation error, which is really complicated if you really want to expose a library and let the users really go wild with various alternatives. Another approach that is library guided is sort of like a partial specialization, but for functions. Again, where the compiler knows to choose more specialized versions over the other. So again, from STL, there's a function called the toAddress that can work either for regular pointers or for smart pointers. And again, it's not really specialization, it's overloading, but the compiler still knows to prefer one over the other. It knows to prefer the second alternative in case you're giving a plain old regular pointer, and go for the first alternative if it's something that's not a pointer and is expected to be a smart pointer. So that's another mechanism that is basically library-based. Whoever wrote the library basically can write their own different implementations, and the application just has to have their classes to meet those specific constraints. Okay. Another approach that is very, very popular in the STL is an approach called the tag dispatch. A tag dispatch, again, is relatively library guided, and here we can see an example of the advanced algorithm in STL, where we take an iterator and want to take it forward n steps. Okay, and we know that some iterators, if we want to take them forward n steps, we need to we can just jump n steps forward by using the plus operator or plus equals operator, while other iterators, they have to be taken n steps, just one step at a time, by calling plus plus it, just like the name of the Italian user group. And the way that STL decides whether to do a plus equals or to call plus plus n times is basically done using the iterator category of each and every iterator. So tag dispatch basically creates several tags. Okay, in the iterator world, they created, I think, 5 different tags, like input iterator, bidirectional iterator, forward iterator, random access iterator, etc., etc. And whenever you call the an STL function and give it an iterator, behind the scenes, the STL implementation will use the iterator category to call another inner function, like the underscore advance, that accepts an extra argument, and that extra argument is the tag itself. And that way, the STL could implement several implementations of the underscore advance function, each accepting a different type of argument as its last argument. That way, basically got a compile time decision of the exact functionality to be called when the user tries to advance different types of iterators. And this notion can be used in other libraries as well. Of course, you basically define different categories, and whatever type of object you want to be templated on should have some traits way to access its own category out of like a menu of options. And inside your library, you implement your algorithm for the different categories themselves. You should note that inside the STL, this tag dispatch is hidden. Okay, it's not part of the advanced function. It's only done inside the underscore advance. So there's no way for the user of the STL to control the iterator category or the type of dispatch that is being done. Technically, it is okay for functions or for libraries to expose it and to have that extra argument as a default argument of their own exported algorithms. And that way, if it's a default argument that's defaulted to the iterator trait of whatever we template on, it can give more power to the user of the library. The user can either just call the library's function, give it the iterator, and know that the default argument will automatically be deduced, or it can try and call the function with explicitly specifying a different category and just see what happens. And it might happen to work or not. The application can have some more power to to dig into the library functionality if they want. And obviously, it can lead to mistakes, but can also lead to sometimes wanted functionality. So those were the mechanisms for a library to tell the application how how it chooses or how it should choose between different implementations of algorithms. There are also a few application guided approaches where the library gives more power to the application to choose what to do. So the first of those is what's called the policy-based design. I believe that the notion was popularized by Andrew Alexandrescu, and we can see a basic use of it in the max element algorithm in STL, where we are templated on a comparator argument, which is our policy. How do we want to compare two items when looking for a max element? And there's a default here that the library chose for us, but if the application wants, they can go and choose whatever they like with a different comparator that should work. And obviously there are both semantic and syntactic rules on what the comparator should do. But if you know what you're doing, then this gives a lot of power to the application to choose how the max element algorithm should work. And this way, by the way, the same application can also look for max element within the same range in different places with different comparators. Okay, the link between the type that you want to run the library with and the algorithm that we were using isn't a compile time fully hardened link. It's something that can be set differently on different call sites within the application code. Another mechanism that is application guided is what's called the customization points, also known since C++20 as CPO, customization point objects. And there's another notion called tag invoke, who some of you might know about. And basically, it gives the library author some way to define algorithms that they want the library users or the applications to specialize. Examples of those are std : swap, or ranges : size, ranges : empty, and there are many more where, again, the library basically says these are algorithms that I would like to be customized on. I might have a default implementation of my own, but I give the application the full ability to control what's going on there. They can. That's usually done via some kind of a specialization, and that's another way for a library to interact with the application, giving a lot of power to the application itself to control what code actually runs within the library's algorithm. CPOs, by the way, if you're not familiar with them, they are objects that typically live like as global variables or inside some namespace, and they have their operator paren defined, and it basically deals with overload resolution in a more specific way than the standard C++ mechanism. I don't know if you've known about it, but writing and using std swap, for example, which is an old customization point from C++ 98, is very, very complicated to do right. You need to do using namespace std, and you need to think about various lookup considerations, because the overload mechanism is very, very tricky in C++, and the customization point objects are the way to basically get around it. If there is an object that's a global or inside a namespace that has operator parens, basically it takes full precedence, and it is the one that the compiler has to call. And inside that operator paren, there is the actual logic that the library can choose to do its own overload mechanisms and priorities, whichever way it likes. You can read more about it, of course, if you look for CPOs or ranges : size, etc. And nibloids, by the way, is another similar concept of objects that are created with operator paren. They're not exactly what CPOs are, but they are sometimes confused with CPOs. So if you find that name, you might, you can think that it might be related. It might be interesting. If one of these things interest you, the other might also interest you. So feel free to look them up. And the last application guided approach that I wanted to talk about, or talk a little bit just to share, enlighten you about, is some new mechanism that is proposed for C++ 23. It was proposed while working on the executors library for C++ 23. As far as I know, the executors are really trying to be fast-tracked into the new version of the language, but specifically behavior properties are not 100% in consensus right now. So there is a chance that executors will get into the standard, but without behavior properties, or the other way around. But I'm not sure. But anyway, the approach here is to have some a function called std : require, where you can give it an object and some tag, some attribute that you want the object to to require, or that you prefer that the object will abide by, and the return value of this require or prefer functions will be potentially another executor that abides by those preferences or requirements. In case it's possible, and otherwise there will be a compilation error. So this behavior properties mechanism is a way where a library can basically choose like a vocabulary of different properties that its own objects, its own functions can implement or can abide by, and the application can, whenever it receives an object from the library, it can ask to make sure or to prefer that one of the properties or some of the properties exist on that object. And if it exists, if it can be done, then you can receive a different object that is basically does whatever you want, and otherwise you can get a compilation error. So that's another mechanism where a library author gives some control to the application. So I'm sure that all these last few slides were a little bit wide-ranging. So to try and give you an overview, here are all of these mechanisms that I talked about in one summary slide, where you can grasp a little bit about how these things are done, where basically there are many different similar mechanisms They can either be used to decide whether some functionality in a library is relevant or not relevant for specific types, or whether different implementations need to be chosen on different types, and whether there's a way for a user code to be hooked into the library code. And we can see that the first three alternatives that we discussed are library-based approaches, where the library can define constraints, and the application just has to usually abide by them. And out of these three mechanisms, that requires clauses in C++20 have as much power as the others. Usually they are it is the most simple. So definitely, if what you want is a library-based approach, and you're in C++20, I would say that the requires and clauses and concepts are typically the simplest way to go. And there's really very little reason to use enable if once you're in C++20, at least in my opinion. Once we go to the application guided approaches, it's more tricky. There, the different approaches have similarities, but also differences. Tag dispatch really gives whoever in the application writes their own type of iterator, their own type of range, their own type of object that needs to work with libraries algorithms. They can choose their own which category their objects belong to. Okay, it's usually within a menu of options, but they have all the choice. And I would say that it's a medium simplicity. Policy-based design is something that is, to some extent, very different. It's more of a runtime than a compile time approach, but still, can give the performance of injecting the caller code into a library in compile time, which is cool, and it's quite simple. So if you want that, then policy-based design are still very, very useful. Customization point objects are again a way for an application to have full power on specific points, which is cool. And sometimes it can, the customization point object will just be a function returning a Boolean, and that way the application can basically choose on/off between some places. Other times it will be a function that actually has some logic in it, and that's a way for the user code and user logic to come inside my library, etc., etc. And the std: require is, as mentioned, a way for a function for a caller of a library to define from a few alternatives what they want to require and what they want to prefer. So that's a lot to process, and it's the end of the second part of the talk. So maybe this also is a good time to stop and see if there are any questions.
Yes, Roy, we have both one question and one comment so far.
Sure.
So I can set the question on the video. So Igor is asking is it possible to make nested concept, for example, in template struct class, only for its methods or subtemplates, not visible outside?
Okay, that's a good question. I believe that concepts, I do not think concepts can be nested inside a class, but I'm not sure. That's a good question. But anyway, regardless, I think that's what you're asking. But in case you're just asking about the ability of putting requires clauses both inside a class and inside methods, then that's totally possible. You can definitely have a class that's templated with some constraint, and some of its methods are constrained with other constraints, and you need to take the the conjunction or the end of both of them in order for a method to appear. But I believe that definition of a concept, I haven't seen it in any way defined inside the class scope, but I'm not sure. Yeah, sorry.
Okay.
Yeah.
And also we have a comment. This is the comment. So concept cannot always replace enable if for substitution, as atomic constraint cannot depend on itself.
Okay.
And we have also a snippet of code. I have not set it to the video, that we have a snippet that can be used to reproduce this.
Yeah, okay,
if you want to examine it, it's I send it to you in the chat.
No,
in our
yeah, it's
chat.
yeah, it's
For
cool.
the future, maybe after the talk.
I
after
believe the
talk.
commenter, and I thank you for the correction. As mentioned, I'm happy to learn from all of you. So great. I also believe that even on the other like on the other side of the spectrum, there are some things that are possible for concepts and potentially impossible for enable if. So yeah, but these are usually rare cases. But thank you.
Okay.
Moving on to our last section about semantics and syntax. It's not a long section, so but I think you'll find it interesting. And to start it off, I should say that semantics are tricky. If you've all listened to Sean's talk this morning, then you might already know that semantics are tricky. So I will quickly go over these two small examples from STL where even the language got it wrong. So first is trivially copyable V for a pair of two ints. So is trivially copyable is a type trait that basically tries to declare or to let us know whether a class can be trivially copied using memcopy, etc. And the semantics are very clear. Is it okay to just move the bytes from one place to another and get a copy? But the syntactic requirements of is trivially copyable were actually defined based on the existence of default or non-default constructors, non-default copy constructors, assignment operators, etc. And the STD pair, for some reasons having to do with templating on references, did not meet the syntactic requirements for is trivially copyable V. And for that reasons, even though semantically STD pair of two ints can be copied, this trait is false for it, and there's really nothing that we can do about it. If we want to change it for new versions of the language, it will be ABI breaking. So as we discussed with Sean, it's tricky to do it, and there is also no way for any application code to specialize is trivially copyable and to decide, yeah, within my application I want to do a template specialization for its trivially copyable V, because although it's okay to specialize templates in general, type traits in STL are not allowed to be specialized unless specifically stated so. And the second example where semantics are tricky has to do with the size method for STD list. Actually, Sean, in passing, also talked about that a little bit, where the size method in STD list has some semantic requirements regarding its complexity. And until C++11, this method could run in linear time or in constant time. And since C++11, there was an extra semantic complexity, semantic requirement for this method to be running constant time. And I'm not sure if you're aware of it or not, but if you're using the STD lib C++ for the one that comes with GCC on earlier versions, you might find yourselves even on C++11 with linear running time STD list side method, because they preferred to be non-compliant with the standard in order to be ABI compatible with older versions. So these are two examples. Here's a short third example of something that well, it's actually like just trying to see how tricky and messy this thing is. When in C++20, the ranges library actually defines a concept called sized range. And what's the sized range? That's a range that also requires the range is : sized t to be defined. Okay, so and that's sort of like a way to see whether a range has a size method or not, or whether you can look for the size of a range. But if you look deeper in the fine print of the definition of sized range, you also see that there's something else called disable sized range. And disable sized range is something that is not a concept. It's a inline context per Boolean expression, which is sort of like an escape hatch. Okay, the people who wrote the ranges library in the standard committee, probably Eric Nibbler was involved. They understood that there are some cases where syntactically, you could call ranges : size, but it won't meet the semantic requirements. It won't run in constant time. So they deliberately created an escape hatch, a context for Boolean, not a concept, called disable size range, that whoever has a range that meets the syntactic but does not meet the semantic requirements of this concept, they can go and define or specialize this Boolean for their class to be true, and that way disable the size range. This is, I think, very, very strange and uncommon it was, at least for me, to see. Mostly because when you look at the definition of the concept, you don't see any mention of this Boolean. You only learn about it if you read the documentation. It's really, really tricky stuff. And another similar example is the borrowed range concept, where again there is an escape hatch. This time it's not a disable escape hatch; it's an enable escape hatch. Another context per Boolean, which is always equals to false. And within the concept of borrowed range, there's this or statement with enabled borrowed range. It's basically a way for whoever implements their own range and want to opt into this borrowed range functionality, they can specialize and do borrowed ranges. So these are two examples where the authors in the STL, they understood that syntactic requirements are not enough, and there is a room for application code to maybe meet the syntax requirements, but not meet the semantic requirements, and give them some way, some escape hatches to basically tell the library, hey, excuse me, I know that things might look okay, but I actually want to opt out or opt into some functionality because of semantics. So these escape hatches are something that we didn't really see before we had concepts. I think one of the reasons that we didn't see them was that because specialization was always possible before C++20 on every type of template. And here concepts are a special case where concepts themselves cannot be specialized. So we introduce these escape hatches, these templates that are not concepts that an application can use. Okay, so we're running out of time, so I won't show you the Herb Sutter's example of another such a concept. I just want to go and tell and show a few more, like one more example where concepts have strong semantic meanings. And here we can see this concept in the STL called equivalence relation. And equivalence relation is actually defined as totally the same as some other concept called STD relation. The compiler itself cannot help us. It does not know which is more specialized, equivalence relation or STD relation. Although if you look at the description itself, it's quite clear that equivalence relation is more specialized than relation, and it's more specialized just purely for semantics, because it's a relation that is reflexive, symmetric, and transitive. We've seen these three requirements just a few hours ago, and but the compiler cannot really help us the way that this concept is worked. And when I read this, I really wondered, why did they do it this way? Why didn't they just add like another end-to-end escape hatch clause? Why didn't they just add some extra Boolean in here and let whoever wrote their own equivalence, their own relation that they know that is an equivalence relation, to try and set it to true in order to tell the compiler, hey, my relation is indeed equivalence and another is not. So it's tricky stuff, and there are several ways to do it. I don't have really a lot of time, but this is a short code example where you can even take a lambda and use some like a mark critical function that turns it into, in this case, a critical code concept. Okay, we can take lambdas and attach semantic escape hatches to them, or semantic warrants to them, which I think can be powerful if you write your own concepts and think that semantics might be important. You can consider adding some of these warrants or escape hatches into your concepts and give your users a way to opt in or opt out in their classes, even in their lambdas, etc., etc. So I don't really have, I think, a lot of time to go into the code, but you can definitely look at it later. I'll post the link to the paper. And I'll just summarize and say that concepts are great. that requires clauses and requires expressions can be used even without concepts. You can put requires with any Boolean that you want, and you can define any context per Boolean with the requires expression, even if it's not a concept. If you're a library writer, I would try and encourage you to give power to your users, build escape hatches, consider using customizations that can be done in call sites. And the C++ standard itself, I think I would wonder why there is no way to specialize concept, why there's no way to specialize type traits in cases that there are blatant mistakes that maybe applications can go and override. So that's my talk. If you have any more questions or comments, I'm really happy to hear and learn. Thank you very much.
Thanks, Roy. Thanks for this awesome session. And we don't have any questions at the moment. I'll give to the attendees a few moments if they have some.
And you can find me on Remo anyway. I'll be on Remo on the
Okay. Yeah. They know. They should know. Okay. Maybe we have one. We take just one. Just one question is this one. Let me copy it to the video. Okay, don't you think that promoting design by contracts with features like C++20 concepts, C++23 contracts, and pattern matching will lead to more ABI breaking changes in large code bases? That's the question.
Yeah, let's let me think about it a little bit. So first of all, I should say that indeed concepts are tricky for libraries such as the STL. It's quite known that it's been said that concepts in the STL are like diamonds. When you write a general purpose library such as STL, whenever you write a concept, it will be very, very hard to change it in the future. So I definitely agree about it. However, I think that in most of our most of the libraries that we use and we write, we have a clear understanding of who our users are going to be, which applications will use the libraries, and many times those users are able to upgrade and migrate from version to version more easily. So I don't. So there is a chance that using these approaches will lead to more API or ABI breaking, but I don't think it should be much of a consideration or much of a problem, especially for libraries that we write on our own. For STL, it's a problem. I agree.
Great, Roy. Thanks a lot again. So, folks, you can follow up with Roy in the networking area afterwards. And if you want to attend Roland's talk about Bayesian computation, stay here on track A. We'll start in a few minutes. So thanks a lot. Enjoy the rest of the conference. We are towards the end, and see you later. Cheers.